So in our last class, we looked at conditional and biconditional statements. We defined them, and then we drew the truth table for the conditional statement. So this is a statement where we have if one statement, then another one. So today we look at the truth table for the biconditional. Okay, so what we take note of is that P, if and only if Q, this is true when P and Q have the same truth value. Okay, so that means if they are both true, then the biconditional is true. If they're both false, then the biconditional is false. But if one of them is true and the other one is false, then that is a false for the biconditional. So you must look at this biconditional as conditional in both directions. So we know that P implies Q. This is true everywhere except where this one is true and that one is false. So if we were to reverse the direction, it means if this one is true but that one is false, then it's false and vice versa, because with biconditional, it just means that it must work in both directions. So if we were to draw the truth table, this is what we would get. We have P, Q, and then P, if and only if Q. So this can be true, it can be false, and this can be true, false, true, and false. So if we look at the statement we have here, it is true when they have the same truth value, and then it is false otherwise. Okay, so the first one, they have the same truth value. So this is true. Here they have different. So we know if this was P implies Q, this would be false, because biconditional means P implies Q and Q implies P. So this one is false because here you have a true statement implying a false one. So that is false. And here they have the same truth value. So it was like the example that I gave that we haven't broken your promise. So I gave the example in class of, I say, if it rains, then we will watch a movie. So let's say, for example, this one is true. So let's say, for example, it doesn't rain and we don't watch a movie. You can't say that I broke my promise. But if it does rain and then we do not watch a movie, I have broken my promise. So that is where we would have a false. Okay, so this one here, false, false is it doesn't rain, we don't watch a movie, I have not broken my promise. I haven't gone against my word. Here it does rain, we do watch a movie, I have kept my promise. Okay. Let's consider the following truth table. So consider the truth table on not P or Q. Okay, so if we were to draw this, we have P here, we have Q there, then we have not P. Okay, so So here we have true, true, false, false. This is true, false, true, and false. And not P is just the opposite. So this is false, false, true, and true. And then here we have not P or Q. So remember with or, if one of them is true, then the statement is true. So here, if I look at these two, Q is true, this one is false, so it means this is true. They're both false, this is false, this is true, and this is true because one of them is true. And you can see this is quite similar. I think you'll recall that this is exactly the truth table for P implies Q. So if you remember P, Q, and then we have P implies Q. So here we had true, true, false, false, true, false, true, and false. So P implies Q. If this is true and that is true, then this is true. If this is true but that is false, this is false. If this one is false but this one is true, this is still true because, like I said, I've not broken my promise. I've just not had the chance to test and check whether I will break my promise. So it's true in the sense that it is not untrue. You haven't shown that I've broken my promise. And if we compare the truth tables here, when P and Q are both true, here we have true, and there we have true. Here, when P is true and Q is false, here we have false and false. And the same thing over here, they're both true, they're both true. So we say that when two statements have the same truth table, as we've said before, it means that they are logically equivalent. So since P implies Q and not P or Q have the same truth table, say that P implies Q is logically equivalent to not P or Q. Okay, and this is helpful. Why do we use logically equivalent statements? Maybe one statement is easier to check than the other. So if you can check or draw the truth table of one, it gives you the same truth table as the other. So when two statements have the same truth table, then we say that they are logically equivalent. Okay, then we can also look at what we call the converse. So if we have our statement here, we have a statement, P implies Q. The statement Q implies P, this is what we call the converse of the statement. Okay, so converse just means you turn the arrow so that it faces the other way. So Q implies P. And then we have not P implies not Q. This is what we call the inverse of the statement. So just negate both of them, but then the arrow remains. And then we have another one, which is called the contrapositive. Now the contrapositive is not Q implies not. Okay, so let's look at the truth table for all of these ones here. So P implies Q, Q implies P, not P implies not Q, and the contrapositive. So we write our truth table with P, with Q. So this can be true, can be false, can be true, false, true, and false. Then we have not P. This is false, false, true, true. And then we have not Q. This is false, true, false, true. Okay, so now let's first look at P implies Q. So P implies Q, we know that one already. If they're both true, then the statement is true. If this one is true, but that one is false, then it means this is a false statement. If this one is false, that one is true, then this is still true. If they're both false, this is true. Then, so we say this is our statement. Of course, these are all statements, but I am going to call some the converse, the inverse, and so on, because they are related to this one here. Okay, so if this is our statement, then we have the converse. The converse means the arrow switches. So you have Q implies P. So we look at Q implies P. If Q is true and P is true, then it is true. But if Q is false and P is true, then this is true. If Q is true and P is false, this is false. So remember, our implication is only false when this one is false and when the first statement is true, but then the conclusion is false. And then here, when they're both false, this is also true because in a way we have not tested whether the promise has been broken or not. So this is the converse. And then we have the inverse. So bad. Okay, so the inverse says not P implies not Q. So not P implies not Q. If this one is false, that one is false, that is a true statement. If this is false and that is true, that is a true statement. If this is true, but that one is false, this is a false statement. And if they're both true, this is a true statement. And then we look at a contrapositive. So the contrapositive says not Q implies not P. So not Q implying not P. If this is false and that is false, this is true because we haven't tested whether the promise is broken or not. If this is true, but this is false, this is false because you cannot have a truth leading to a lie. If this is false, and here we have a truth, this is true. And if they're both true, this is true. Okay, now we want to look at these four statements, the statement itself, the converse, the inverse, and the contrapositive. Are any of them logically equivalent? So if we look at this first row, everything is true. This one is false. These two are true. So obviously the statement is not logically equivalent to the converse. It's not logically equivalent to the inverse, but here they're both false. And here, when it's true, that is true. This is true, that is true. So we can see that a statement and its contrapositive are logically equivalent. Okay, so they have the same truth table. This means that they are logically equivalent. So an example of this is if you are in Namibia, sorry, if you are in Windhoek, you are in Namibia. Okay. So this is our statement. So we can come up with some other statements and label them the converse, the contrapositive, and the inverse. So the converse would be if you are in Namibia, here I should put then. then you are in Windhoek. Well, this one is obviously not true. If you are in Windhoek, you are in Namibia, this is a true statement, but this one here is obviously not true. Being in Namibia does not necessarily mean that you are in Windhoek, so the converse is not true. Then we have the inverse. The inverse is if you are not in Windhoek, then you are not in Namibia. So again, this is not logically equivalent to our statement, because not being in Windhoek does not necessarily mean that you are not in Namibia. Okay, and then the contrapositive is if you are not in Namibia, then you are not in Windhoek. And this, of course, we know is true. You cannot be outside of Namibia but still be in Windhoek. And we can see that a statement and its contrapositive are always logically equivalent. Okay, and then the converse and the inverse, these are not logically equivalent. Then we have a theorem. So this is just a summary of what we have done, and we summarize it as a theorem. So the theorem says that a conditional statement, P implies Q, and its contrapositive Q implies not P, are logically equivalent. Okay, so this is a summary of what I have been stating up here, and we summarize it as a theorem. Okay, so another example of this. We consider this statements. So we have a statement P implies Q, which says that if A is equilateral, so you have a triangle A, equilateral, then A is isosceles. Okay. And the converse, Q implies P, says if A is isosceles, then A is equilateral, which is not necessarily not necessarily true. The first one, yes, it is true. If it is equilateral, then it is an isosceles triangle. Okay, so here we can see that, or we can take note that P implies Q is true, but its converse is not. The converse, which is Q implies P, is not true. So it is false. It is false. For example, here we say let x be an integer. Do we prove that if x squared is odd, then x is odd? Okay, so here is a question. It says, if you have x, which is an integer, how can we prove that if x squared is odd, then it means that x is odd? So it might be tricky or difficult to actually prove P implies Q here. So our P is x squared is odd, and then our Q here. So here we have P is x squared is odd, and Q is x is odd. Okay, so that might be difficult to do, probably not impossible. So what do we know? We use what we know about statements and their contrapositive. So we could, instead of proving it directly that P implies Q, what we can do is rather prove that not Q implies not P, and that is proving that P implies Q, because if we show that the contrapositive is true, then it means that the statement itself is true. So here we are going to prove that not Q implies not P. So this is where contrapositives come into play, because sometimes they are much easier to prove than the statement themselves. Okay, so not Q implies not P. This means that we were showing that if the integer is not odd, that means it's even, then x squared will also be even. Okay, so we'll let x be an integer. So this is the proof. Let x be an even integer. Okay, so remember, we want to show that x is not odd. That means it is even. So if it is even, it means that we can write x is equal to 2 times n, where n is an integer. Okay, so if x is an even number, all even numbers are multiples of 2. So if it is a multiple of 2, we can write it as 2 times something. It doesn't matter what that something is. If it's 8, if x is 8, then we can write it as 2 times 4. If x is 12, then it's 2 times 6. If x is negative 12, it's 2 times negative 6. So every even integer, you can write it as 2 multiplied by something, and that something, we're calling it n. Okay, so we started with this part, not Q. So x is even. Now we have to show that when I square it, my answer is also going to be not odd. That means it's going to be even. So this means that x squared, this is equal to 2n squared, and this is 4n squared. And 4n squared, I can write it as 2 times 2n squared. Okay, now this 2n squared, we know that since n is an integer, this means that n squared, in fact 2n squared, is also an integer. Okay, so if you take any integer and you multiply it by itself, and then that answer you multiply by 2, you're still going to get an integer. And then we can call it, say, m. Call it m. Okay, so this means we actually have x squared is equal to 2 multiplied by m. M is an integer. This means that x squared is even. Now, if x squared is even, because we are writing it as 2 multiplied by an integer. Okay, so x squared is even, and that is the end of my proof, because remember, what we wanted to do is show that if x is even, then it means that x squared is even, and that also proves that if x squared is odd, then x is even. So we have proved the contrapositive. the contrapositive, which is also a proof of the statement itself. Since they are logically equivalent. Okay, so we can say that if x squared is odd, then x is odd. Okay, so we've proved this not directly, but indirectly by using the contrapositive. Okay, then the next thing we look at are what we call arguments. An argument is a relationship between a set of propositions. So you have your propositions P1, P2, all the way up until Pn, which is called the premises. And another statement. The conclusion. Okay, so instead of just having like one, of course you can have one, but it may be more than one premises. And then you have another one, conclude another statement Q that you combine these ones in some way and then implies another one. Then this Q here, this is our conclusion, and then the combination of these ones is what we call the premises. Okay, so this is denoted as follows. So it is denoted by, say, P1, P2, and it goes on to Pn. And then we have the symbol here with the conclusion Q. And then we say that our statement, our argument rather, we say that an argument is said to be valid if the premises yield the conclusion. Okay. So when you put all of them together and then you get that one, then that is what we that is when we say that our argument is valid. And here we have a definition. We say that an argument is valid if Q is true. Whenever all the premises P1, P2, all the way up until Pn are true. . And if an argument is not valid, we call it a fallacy. Let me say that an argument that is not valid is called a fallacy. Okay. So if it's valid, it means that Q is true whenever all our premises are true. And if that is not the case, then we say that our argument is a fallacy. Okay. And that's about everything we need to know on the truth table, and logical arguments, logic and truth tables. So for the next couple of minutes, we're going to go over some exercises, types of questions that you will see and how to answer them. Okay, so example number 1, it says, let P be, it is cold. So this is our statement P. And let Q be, it is raining. Okay. Now what we want to do is to give a verbal sentence that describes the following. So we want to say in words, what does not P mean? What does P and Q mean? What does P or Q mean? B, what does Q or not P mean? And what does not P and not Q mean? And what does not Q mean, or what are they in terms of our sentences? So this is a typical example of a type of question that you will get. So here I have labeled the statements for you. Sometimes I'll just give you the sentence. The first sentence will just say it is cold. The other one is it is raining, and then I say give me variables. So you say, okay, my first variable P is going to be it is raining, and then we let Q be it is cold or something like that. All right, so not P, what does not P mean? If we write a sentence, this would be it is not cold. So it is not cold, or you could say it is false that it is cold, but of course saying it is not cold sounds more grammatically correct. So try and always write the sentence that sounds more grammatically correct. Okay, P and Q would be it is cold. So P is it is cold and raining. So it is cold and it is raining, as long as I see that you understand that this symbol represents and. Then the third one, P or Q, it is cold, or it is raining. And then the fourth one, Q or not P. So what is Q? Q is it is raining. So we can write that one first. It is raining. And not Q or it is not cold. Then number 5, not P and not Q. So P says it is cold. So not, or the negation of that would be it is not cold. And it is not raining. Okay, so that is how you write that one. And then not Q, you could say something like it is not true that it is not raining. Okay, so that is how you could answer that one. Then if we look at another question, this one is on drawing truth tables. So the question would say, draw the truth table. Of not P or not Q. So we start with P, Q. This is true, true, false, false. Then we have true, false, true, and false. Then we need not Q. Then we need to work out P or not Q. And then we need the negation of P or not Q. Okay, so this is what we need. So not Q, this is false, true, false, and true. Make this nicely. And now or, we look at these two. If one of them is true, then the whole statement is true. So this is true. This is true. They're both false, so it is false. This one is true. And then the negation of that, just negate this one. This is false. This is false. This is true. And this is false. Okay, so this is what we have. Another one, number 3. It says verify that P or not P and Q is a tautology. So you have to remember that a tautology is a statement that is always true. So it doesn't matter what the values, the truth values of P and Q are, our statement is always true. So to verify this, we just need to draw the truth table. So we have P. This can be true. And we have Q. Then we look for P and Q. So remember, BODMAS still applies here. So P and Q, they must both be true in order for it to be true. If one of them is false, then it is false. And then the negation of that, P and Q. This is false. This is true, true, true. And then P or P and Q. Here, one of them just needs to be true. So this one is true, that is false. This is true. They're both true. These two are true, so this is true. So we can see that since P or not P and Q is always true. It is always true. It is a tautology. Okay, so that is what a tautology is. It is always true. And a similar question, number 4. We verify that P and Q and not P or Q is a contradiction. So again, to prove this, just draw the truth table. We're going to start with P and Q. So both of them must be true, otherwise it is false. Then we look at P or Q. One of them must be true. So here, this one is true, this is true, this is true, and this is false. And then the negation of that, this is false, 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 and true. And now we look at the conjunction P and Q and not P or Q. So we're looking at this one and that one. So if one of them is false, this is false, this is false, this is false, and the last one, because that one is false. And you can see that for its truth value is always false, then it means that it is a contradiction. Then another question. So remember, this means that they are logically equivalent. It means they have the same truth values. So we can draw the truth table P and Q. So we have true, true, false, false, true, false, true, and false. Then we have not P, not Q. We have not P and not Q. And then we have not of not P and not Q. And then we also have this one P or Q. So we want to show that these two last columns have the same truth values. So here, this will be false, false, true, true. This will be false, true, false, true. Then here, the conjunction, they're both false. It is false. If one of them is false, it's false, false, and this one is true. Then the negation, this is true, 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 and false. Okay, and then P or Q, just looking at these two, they're both true. So it's true. One of them is true, it's true. One of them again is true, it's true, and they're both false, so it is false. And when we compare these two, they have the same truth values. Therefore, these two are logically equivalent. one or two more examples. So here it says, show that P if and only if Q is equivalent to P or Q implies P and Q. Okay, so here all we need to do is draw the truth tables of both of them and then compare them. So we have P here, we have Q. So this is true, true, false, false. Can be true, false, true, and false. Okay, then we look at P if and only if Q, if they're both true, it's true. If one of them is false, then it is false. And if they're both false, then it is true. Okay, and now we look at P or Q. So P or Q is only false when they're both false. Otherwise, it is true. And then P and Q. P and Q, it is true when they are both true. Otherwise, it is false. And now we look at P or Q implies P and Q. Okay, so if they're both true, then this is true. If this is true and that one is false, then this is false. If this one is true, that one is false. It's the same thing. It is false. And if they're both false, then this is true. So now we compare. Here it's true. There it's true. False, false, false there, false there, true and true. So we can conclude that because they have the same truth table, then they are logically equivalent. To determine the contrapositive of each statement. So the first one says, if John is a poet, then he is poor. Okay, so if John is a poet, then he is poor. The contrapositive would be if he is rich, if John is rich, then he is not a poet. Okay, so that is the contrapositive. So when I'm writing these statements, try and figure them out for yourselves. You can pause the video and then see if you get it right. The second one says only if Mark studies, will he pass? Okay, so here it might be a little bit confusing when it starts only if Mark studies, will he pass? This is actually another way of saying if Mark passes the test, then he studied. Okay, so only if Mark studies will he pass. So it means if he studied, then he will pass. No, that's not right. Only if Mark studies will he pass. Okay, that is the same thing as saying if Mark passes the test, then he studied. Okay, so this is, I'm writing it in red just to write it in the standard form where if this happens, then this. So this is the same thing as saying Okay. If Mark passes the test, then he studies. Okay, so the contrapositive of this will be if Mark does not study, then he will not pass the test. Okay, so this one might be a little bit tricky, but we need to remember what only if means in terms of our statement. So if you go back in your notes, I think somewhere where I wrote it, let me just read it. I can't see the notes. So this is what we wrote. You go back in your notes, you will see it. So it said, so something to take note of. It says that P implies Q. What's happening with my marker? P implies Q means Q only if P. Then another one. If X is less than 0. Okay, this is less than 0. Then X is not positive. Okay, so if X is less than 0, then X is not positive. The contrapositive would be if X is negative. Okay, no, if X is not positive, that means it's negative. So we say, I need to write this down. We say if X is not positive. Okay, so I'm just gonna write it like that, and then just to demonstrate my thinking process, not positive, then X is less than, X is not less than 0. Okay, so this is how you should think about it. And then what you write not positive, this means it is negative. Okay, so we say if X is not negative, then X is not less than 0. Okay, and then you can say if X is not negative, means it's positive. So the contrapositive, you can also write if X is positive, then X is not less than 0, which of course makes sense in saying the same thing as that one over there. Okay, so I think that is all the examples we'll look at. So with that, we are done with truth tables. In the notes that are there on Teams, you can see there's more examples. Please do go through them. If you have any problems, then we can discuss those in class.